I was looking at the homework and trying to think of what things might be useful or helpful, kind of hints to you all. One thing that we talked about, but I realized that maybe this might have gotten missed, is this idea that the total strain energy in your structure is kind of the sum of all stretching, bending, torsion, all those things. But if you take a structure like, for instance, if you take a structure that looks like this, the total strain energy in this structure, we'll call the total strain energy V. If we assume that, I think this thing is loaded in such a way that I forget where the loads are, but it doesn't really matter for the point I want to make. I think this is loading in such a way where bending is going to be the primary deformation. And in that case, you kind of can think of the structure as like, I've got one beam here, and I've got one beam here. And so then therefore, the total strain energy in this beam, actually I'll make this a little bit more clear. The total strain energy, U, not potential energy, so the total strain energy would be just the bending energy of each of these beams added together. So that was one of the first things I thought is the strain energy in this structure can be thought of as the strain energy in the parts that compose the structure. So if you just add those things up, you get the total strain energy in the structure. This might be obvious, but if it's not, I thought it might be a nice hint for the homework. And because a lot of the things in the homework look a little bit more complicated than a simple beam sitting on two pillars. But I wanted to kind of make this point that you can take the total strain energy in this thing here as being something where you just sum up all the strain energies of the various parts. In a way, you're kind of doing a really lazy integral, right? You're basically saying like, I'm going to split this into two parts. I'm going to sum over those two things. You could split this into an infinite number of parts. You know, you could split this beam up however you'd like and sum up over all those. You get the same result. But this is one of the first things I thought might be helpful for the homework. One of the second things I thought looking over the homework was, as always, this is probably true with mechanics of materials. There's a point in the beginning of the semester where you realize how you have to go back to statics and remember a lot of this work is going to be recognizing the moment is a function of P and X and where you are. So you're going to have to go back and do some statics to realize, like, okay, if I'm pulling on this thing, the moment in this bar is going to be the force times where I am. But then the moment in this bar from that vertical force is just going to be the force times this distance. But then if I have a force over here, I do the same thing. And now I have to worry about, all right, where am I over here? All of this comes down to, do you remember how to split up from like force balance, moment balance, to figure out what the moment in this beam is? Because most of this stuff isn't hard. You just need to take the moment, square it, and then take derivatives of that with respect to your force P. That's Castigliano's theorem, right? You're basically trying to take m squared over 2EI and then take the derivative of that with respect to your load. So I thought this was kind of one thing that might help going back and reviewing your statics to calculate what the moment's going to be. This is just a fancy way of saying the moment should be some function of force and distance, and maybe it's going to depend, on some location where you are. That's true also for like the more complicated structure that looks like this, in which I think there's a load over here. And so you're going to have to remind yourself that, like, you're going to need to calculate what's happening here, calculate what's happening, you know, from the to the right of the load, calculate what's happening to the left of the load. But the point I want to make is, you know how to do this. This is just like, okay, I have a force here. I'm being asked about something down here. Castigliano's theorem tells me that in order to do that, I have to add a fictitious load over here. And then once I add that fictitious load, I calculate the beam one, I calculate the moment in here, I calculate the moment up here, the moment up here, the moment down here. And knowing that I can split this thing up into different segments, I can calculate what the total energy is going to be. So these are a couple things I thought might be helpful as you're going through the homework. Recognizing that you can split the structure up and sum up all the components. Remembering this part, which I'm sure you've seen so many times now, but then also probably could use a refresher on it. So, you know, dig through your statics or mechanics of materials notes. Yeah, these are the things that jumped out at me when I was looking at the homework and things that might be helpful. I know that the jump from like a beam to a structure can be kind of intimidating, but that's why I think this energy process is that's why I think this energy process is helpful, because you really can just kind of split this whole thing up here and sum up these things as components. And you don't really have to worry about like, how is this combining with that thing? You just have one structure, and you're splitting it up into components that are hopefully easy to analyze, and then adding them all together. All right. Any other questions jump out on that? I don't think it'll be too bad. All right. So thinking back to what we've done and where we're at today, we started by defining a strain energy. And then last class, by just doing dimensional analysis, we said, okay, our strain energy, the units of our strain energy is a Newton meter. And just by looking at that, we recognize very quickly that if I take derivatives of my strain energy, say with respect to length, then I'm going to get something that's going to be a force. And we use that to derive one of Castigliano's theorems, which says that we can find the reaction force at any point by differentiating the strain energy with respect to a length. And then we flipped it, did the opposite. We said, well, I can also take the derivative of the strain energy with respect to my force, and I'm going to get a length, which is how we're using the other Castigliano's theorem, the second theorem, which says I can calculate what the deflection at any point in the material that I want, just by taking the derivative of my strain energy with respect to a force that's acting at that point and in that direction. That's because those are Castigliano's theorems. The two theorems are basically, which one am I differentiating with? Am I differentiating with respect to length? Am I differentiating with respect to force? This can also be extended to differentiating with respect to a moment. Now, a moment has the units of force length, so differentiating with respect to a moment is going to give me something dimensionless. That's an angle or a rotation. And if I differentiate with respect to an angle, which is dimensionless, this doesn't change. I end up with Newton meters, which means that it'll tell me what the moment is, or the reaction moment at a support. Those are the same theorems, the Castigliano's theorems. But there's something deeper at work here, which may be obvious to you, but it may not. If I take the derivative of my strain energy with respect to a length, I get a force. Equilibrium tells us that we require the sum of all the forces to be equal to 0. So another way to think about equilibrium, if you're starting from a position of energy, is that if I simply take the derivative of my total potential energy with respect to I'm going to write this as kind of a generic degree of freedom distance. We're going to call it Q. But it's going to be either a displacement or an angle, depending on what's happening in your problem. There could be more than them, so you would do it for all of them. If I take the derivative of my total potential energy with respect to the degree of freedom in my problem, either a displacement or a rotation, and I set that, which we know this is going to be a force, right? This is either a force if Q is a length, or a moment if Q is an angle. So taking the derivative of my total potential energy with respect to my degree of freedom is going to give me either a force balance or a moment balance. And we know that the sum of all the forces or the sum of all the moments has to equal 0 for our object to be in equilibrium. So this is another way of finding equilibrium equations, determining if your structure is in equilibrium. If you can just write down all the strain energies in your problem and all the potentials from external work, right? Because we had to remind ourselves, what's V? V is the strain energy plus the potentials due to external loads. And a potential is the opposite of the work, right? It's the negative of your work. So if I can just write down the total potential energy in my system, and I differentiate it one time with respect to either some displacement or angle, and set that equal to 0, I have the equations of equilibrium for my system. This makes sense? This is pretty, I think, at least a pretty straightforward extension of what we did last class. The nice thing about this energy approach is that it allows us to evaluate the character of equilibrium, which is not something that we really spent much time talking about as engineers up until this point. So what do I mean by the character of equilibrium? Well, let's see here. A lot of times, if you ever, this is true if you're doing graduate work in structural mechanics, if you're working at a company doing finite element solutions to problems of structures, this concept that we're going to talk about right now will crop up kind of anywhere if you're doing things with solids or fluids. And it's this idea that equilibrium is only one part of the puzzle. So let me explain what I mean. So here's the simple, one of the ways people talk about potential energy is they talk about it in this vague wording. They'll say there's a potential energy landscape, which is I think when you're first exposed to that concept, it doesn't really make a ton of sense what they mean by that. And it's actually really useful to think of potential energy as like a topography, like literally as like the contours of the ground, and to picture a ball in that topography. And what I mean by that is this. So here is my potential energy landscape. It's a bowl. I'm not saying it's like a bowl. I'm saying it's literally a bowl. Like, let's pretend you have a bowl, and you're going to put a ball in that bowl. The character of our equilibrium, whether it's stable, unstable, or neutral, is determined by what happens when you kind of imagine a ball on that landscape, and you imagine just poking it a little bit. And you say, okay, how does it respond? This is the fancy mathematical way of saying this would be, how does it respond to an infinitesimal disturbance? And what that means is, take that ball, poke it a little bit by a displacement delta, and ask what happens. What happens here is once you remove, so you poke it a little bit and you move your finger, it's gonna slide back down, oscillate around here, and eventually come back to a stop exactly where it started. This is what is referred to as stable equilibrium. You can do the same thing, but instead this time, you can imagine putting your ball on top of a hill. And here, these are the types of equilibriums that we don't talk a ton about. Here, if I put my ball on top of this hill, and I poke on it, it's pretty clear what's going to happen. That ball is in equilibrium. If I do a force balance, you know, there's the forces are balanced. There's no, the sum of the forces equals 0 here. This ball is perfectly in equilibrium. It's just in an unstable equilibrium because any infinitesimal disturbance will change the location of this ball, and instead of it returning where it came from, it'll go somewhere far away. We don't really care where it goes right now. What we care is, does it come back or not? And it doesn't come back. If I poke this thing, it's going to roll off. This is an unstable equilibrium. Yeah, sorry, that is my delta symbol. So that is a displacement delta. So I'm saying perturb it by a small amount delta. That symbol actually is kind of important because we're going to get into some of the more advanced mathematics that describe these things. And that symbol kind of plays a really important role in that math. So this is a lowercase delta. The third one's kind of boring, but you can certainly possible to imagine that I just put my ball on a plane, and And here's what I mean when I say, you can think of this literally as in a bowl, on a hill, or on a plane, because the potential energy of this ball, if you think about it in terms of, say, a gravitational potential energy, is dictated by how much you're lifting it up or down. If I take a ball and I put it on this neutral plane, and I perturb it, poke it, perturb it, displace it, whatever you like, then it stays in that same plane. It doesn't change the gravitational potential energy, right? There's nothing that's changing if U is mgh, where h is the height of this thing away from the surface. Changing this one lowers the potential energy. Pushing this one up the hill raises the potential energy, so it wants to go back down. Pushing this one doesn't change the potential energy at all, so this is what's referred to as a neutral equilibrium. For those of you who really enjoy, calculus, you might start to pick up on some of the connections to the shapes of these planes and some of the operations you would do in calculus. What I mean by that is, come back over here. This is saying, I'm looking for a point where my curve is either a maximum or a minimum. So if I'm plotting like literally, I'm just going to plot what I'm saying here. If I'm plotting V, let's see here. And I guess we can say this is delta. We can say this is 0. We could translate this little stable equilibrium graph to an actual plot. And if I was to ask you to find the minimum of that plot, and I gave you a parabola, this is like whatever, minus x squared, what you would do is you would take the derivative of that plot, set it equal to 0, and solve for the point at which this thing's the minimum, which is exactly what we're doing. If I was to ask you if that curve is concave or convex, how would you solve that problem? No one remembers? Come on. This has got to ring some bells.
Take the second derivative.
Yes, perfect. Thank you. Second derivative. The second derivative of this thing tells you, from the sign of that second derivative, it tells you whether or not this thing is curved this way or curved the other way. Remember, the first derivative, we often kind of misuse a term. And we say, I want to minimize my function. Minimize. I want to minimize. I'm going to take the derivative of my function, set equal to 0, and I'll find the minima. That's a misleading term. It's a misleading term because if I was to ask you to take this other problem, so if this is I, and this is II. If I was to ask you to take this other problem, let's not do it on the same graph. Here we go. If I was to ask you to find the peak of this curve, you would do the exact same thing. You would take the derivative of my function, set it equal to 0, and you would find this point. So taking the first derivative of your function, setting equal to 0, doesn't minimize it. It's got a more annoying term. It extremizes it. It tells you, all it can tell you is you found something that is either a minimum or a maximum. If you want to know whether it's a minimum or a maximum, you have to check the second derivative. And the sign of the second derivative will tell you if it's a minimum or a maximum. So let's calculus review here. If I have a function f of x, I can take the derivative of that function f of x. I'm noting my derivative with the apostrophe here to note that I'm taking the first ordinary derivative of my function f of x, which is just generic right now. It's just, in this case, I'm just drawing parabolas. And I'm setting that equal to 0. So the second step is if I want to know if I have a minimum or maximum, then I check the second derivative of my function. If my second derivative of my function is greater than 0, in the structural mechanics terminology, they would say if the second derivative of my total potential energy is positive definite, you can just file that away as something you delete until it's more useful to you. But it's the same thing in terms of what we need to worry about here. If it's positive, then our curve is, I'll be honest with you, I can never remember which one's convex and which one's concave, so I'm just going to draw. If it's positive, it means it's this one. And if it's negative, it means it's this one. So these are the calculus terms, but we need to translate this to our structural mechanics world. So give me a second, move some stuff around. So in our terminology, the first derivative in which we're extremizing, or finding the extremum of a function, this finds us equilibrium. Our second idea here of determining whether or not that equilibrium is convex or concave, or it's a minimum or a maximum, in which case we're taking the second derivative. I'm just going to highlight those really quickly. Checking the second derivative in the case of structural mechanics tells you if that equilibrium is stable. Questions? Nothing? Is this? It's all right?
I have a question.
Yeah.
So for the stability, like is one like the positive one gonna be like the never mind, answer my own question. Like the positive one's gonna be the stable equilibrium, right? And the negative is gonna be unstable.
Exactly.
Gotcha.
That's exactly right. Stability gets a little bit more complicated than this, and this is especially important to, at least at this point in your careers, be aware of, and kind of this should be something in your brain that helps you ask questions. Answering these questions is not necessarily easy, but these are the questions to be thinking about asking. I explicitly use the word infinitesimal disturbance. I said poke it a little bit. What we're describing here is what's known as stability in the small. That's because we're just poking it a little bit. You can imagine more complicated landscapes. In fact, you can imagine landscapes as complex as you like, and they in fact get this complex. But you can imagine a landscape like this. Let me see if I can draw this. Where in this landscape, if I place a ball in the top of that dimple, then now the size at which I poke this really plays an important role. So for instance, it should be fairly clear to you that if I poke this a small amount, it'll come back to rest here. So this is what we refer to as stable in the small, but unstable against large disturbances. If I push hard enough, this thing becomes unstable. So this is a minimum, but it's not a global minimum. You'll hear this term a lot in all aspects. This is what makes protein folding really challenging for computers. This is what makes almost any and all computational simulations of structures that could become unstable. This is what makes them hard, is because it's very easy to find a minimum. It's very hard to find the global minimum. So this is a local minimum, which means there's a little dip here. It's definitely a minimum. If I poke it a little bit, it'll stay in there. Poke it a lot, it's going to change. I'll give you another example. So here, I can place my ball on the top of this potential energy landscape. And again, you can just be thinking about this in terms of gravity. Your potential energy is changing due to simply gravitational potential energy, which is dictated by the height of the ball. In this case here, this structure is unstable in the small, but stable in the large. Poke a little bit, it's going to roll off. But then you get here, and this thing is going to be robust against really large disturbances in either direction. So it's unstable in the small, tiny perturbation will change change the potential energy of our system, but it's going to find another happy place. So this is in the small, unstable in the large. This one and vice versa. Unstable in the small. And it's stable in the large. what I mean by this idea of local minima versus global minima is you know, you might be in some sort of what's referred to as a metastable state. Where your ball starts up in this top ramp up here. And you found yourself a nice local minima. And if you're the modeler, you might not be aware that there's another minimum not that far away. And this is what's referred to as metastable. It's kind of stable in each of these cases. It can be poked back and forth with a little bit of effort. I'm bringing these up mainly for you to be aware of these issues that crop up in structural modeling, which is that it's very easy to find local minima. It's very hard to know and to be certain that your local minima is also a global minima. At this point in your career, the important thing for you to do is to know this and to be asking these questions. If you're ever, even if you're asking them of yourself, like you run a simulation, find an element model, and you see a structure buckles and forms this crazy shape, the first thing you should ask yourself is like, I wonder if that's actually the shape it's going to find, or maybe if it got trapped in some local minima, and it'll never get there. I did my simulation with some missing information. At this point, that's where I want your head to be at, is just knowing conceptually how to think about stability in terms of I can find equilibrium by taking the first derivative of my total potential energy. I can find the stability of that equilibrium point by taking the second derivative of my total potential energy. But then there's kind of another more complicated layer to it that you should just be aware of, and that is these types of diagrams here, that it can get more complicated, and that's where I want it to be right now for you. Questions about stability? We're going to go through some examples of this today. We're going to go through them with really discrete, like very simple structures, even more simple than we've done in like a mechanics and materials course. Because to do this with more complicated structures requires us to learn some new mathematical techniques, which we will do. But I want to first get you comfortable with the concepts, with the simple, straightforward mathematical techniques. Then we can move on to how we actually handle this in a continuous system, because it's a bit trickier. I suspect this type of stuff will be easier if I can provide you an example. So let's do an example. Let's do the simplest example I can think of. It's barely, I guess it's a structure, but at the very least, it's something you're really intimately familiar with, and that is a pendulum. So let me draw here pendulum. I'm going to draw my pendulum. Sorry. So here, gravity is going down. My pendulum is up at some arbitrary height. We're going to measure the angle away from the vertical. We'll say that my pendulum has a fixed length L, and the ball and we'll say that L is massless, and the only mass in the system is that ball at the end of my pendulum, and that has a mass of magnitude m. If L is fixed, L is just a rigid bar holding my pendulum, then simple geometry can tell us what the vertical projection of this pendulum is. Remember, that's what we care about. We want to know how much, oops, I can't use that color. Let's do, we want to know this height as a function of angle, right? Because that's the vertical component. Gravity's only acting on that vertical component. And so the potential energy on our system is going to depend on how much of my pendulum is being projected into that vertical component. Simple triangle, right angle. This is the length of my pendulum times the cosine of theta. And we know that the total potential energy in this gravitational system is just going to be the mass times gravity times the amount, this length here, oh, you can't see at home, this length here, which is the component of the kind of angle that gravity is acting on. So that means our total potential energy I'm going to write this a little bit more mathematically correct. Our total potential energy only depends on the angle, because that's the only thing that's changing in our problem. And it can be written as mg times the height, but in our case, the height is going to be that vertical projection, L cosine theta. So we can check the equilibrium points of this pendulum really simply. We just take the first derivative of our total potential energy with respect to our 1 degree of freedom. Our 1 degree of freedom is theta. So I can say, if I take the partial derivative of v with respect to theta, it's not really a partial derivative. In most cases with structural mechanics, it is a partial derivative, but here we only have theta. So technically, this is just an ordinary derivative. And I say that's just going to be simply negative mgl sine theta and equilibrium requires us to take the first derivative of our total potential energy with respect to our degree of freedom and set it equal to 0. And so I'm left with asking the question, what angles give me this side of the equation equals 0? Pretty simple. All we really care about is this. And this says that the only thing that can be 0 here is sine theta. And sine theta is 0 at theta equals 0. And theta equals 180 or pi. Now, from our intuition, we know that only one of these is a stable equilibrium point for this pendulum. Intuition doesn't get us too far once we start working with more complex structures. So how do we prove which one of these states is stable and which one's not. And what we do to prove that is we say, okay, I found my equilibrium configurations. There are two. By just taking the first derivative of my total potential energy and setting equal to 0. I can determine the stability by checking the character of that equilibrium point, which requires us to look at the second derivative. Again, in this particular case, it's an ordinary derivative. Second derivative is also pretty easy. It's just negative mgl cos theta if I put in, so here's a little bit, I guess this might not be as obvious to all of you. I mean, at least I always have to double check myself. But what I do at this point is I can say, what is the sign of this term when I put in my two equilibrium conditions? So I can say, what's the sign of this term when theta is equal to 0? And what's the sign of this term when theta is equal to pi? Now, theta equals 0. Cos theta is equal to 0 is equal to 1. This has a negative out front. So theta equals 0. My second derivative is definitely negative. So this is unstable. And theta equals pi gives you -1. -1 times negative gives me a positive number. Make some room here. And so we found what matches our intuition, which is that when the pendulum is at an opening angle of pi, it's stable. Some of you might be wondering, okay, we talked about stable and unstable. What is happening with this neutral equilibrium point here, which we really kind of lost? And what's happening is, you can just kind of see it right down here. I'm checking two things. I'm checking the sign of my second derivative. But the third option is that the sign of my second derivative is not greater than 0 or less than 0. It's exactly equal to 0. If it's exactly equal to 0, in that case, we have a state of neutral equilibrium. Generally with structures, if that happens, which I would say is very rare, I work on stability problems for the bulk of my entire research. This doesn't happen often. If it does happen, what you do is you check the next level of your derivatives. You check the third derivative of your total potential energy. You check the sign of that. Just file that away. It's not important. But the neutral equilibrium comes from when the second derivative is exactly equal to 0. Pretty reasonable so far, yeah? Why don't we take a break and then we'll do another example that is a little bit more structure related. And yeah, so let's take a break until, I don't know, let's do 5. Let's do like 9:58. And if you have any questions in the meantime, you can feel free to shout them out. I'll be just standing over here.
Professor, can you zoom in on the last derivation that you did at the bottom?
Is that all right?
Yeah, thank you.
I know my handwriting is small. I'm really sorry for those of you who are, please feel free to ask me to zoom in whenever. I've tried to write bigger and it goes really poorly. So I will happily zoom in at any point, but I'm very aware of my flaw there.
And could you also explain how stable is surrounding both unstable and stable? If that makes sense. In the blue, you have it referring to both conditions.
I didn't mean to write that. I meant to write, sorry. That was just terrible. I meant to write stability.
Oh, okay.
Sorry about that. Thanks. Yeah. So this was mainly to say the top portion is how you calculate equilibrium. The bottom portion is how you calculate stability. I missed, that was a miss right there. Thanks for catching that.
No, no worries. Thank you. That makes sense.
All right. Should we get back to it? For those of you who dove into the SI of that review paper, I talked about the kind of two simplest instabilities, simplest possible buckling instability and the simplest possible snapping instability. And I want to go through those here because they provide another example of how to use these energy methods. And they also start to build up the complexity, what kind of layer the complexity of these things. This first one is the simplest version of Euler buckling, even simpler than what we did in mechanics of materials. In my opinion, this is the way it should be taught at that level, but whatever. This we'll do it here instead. It's referred to as a hinged cantilever or a hinged column. Let's say hinged cantilever. And the reason why it's simpler is because we're going to take a rigid bar and at the base of this rigid bar, we're going to add a rotational spring. If you have a hard time imagining what a rotational spring is, you could equivalently draw it like this. So we have a rigid bar on a pin, and you can imagine a spring kind of there that's restricting its deflection. You could imagine like one on both sides, where like if it's kind of a tilted spring and you push on it, it's kind of storing energy the more you rotate it. That's the picture I want you to have. They're the same mathematically. This is a length L. And regardless, I'm actually going to move these around so that way. And what we're going to do is we're going to take we're going to apply a load. P. And again, just like we did in the last case, we can measure our angle away from the vertical. Oops. And we can ask, what's the total potential energy of the system? What are the equilibrium points? And what are the stability of those equilibrium points? I'm going to write it in a little bit more mathy way, in which we can say the total potential energy, V, is going to be a function of two things now. So this is different than the last problem. In the last problem, the potential came from gravity, a body force acting on this. In this case, the potential is coming from a point. So we're going to say that the total potential energy depends on two things. It depends clearly on the angle. The more it's rotated, the more energy you're storing in that spring. Okay, so V depends on my angle, theta. And it's also going to depend on the load that I'm applying, P. Our strain energy, which is the only way we're storing energy in the system, is we're storing energy in the spring as we rotate it. That's all. So the strain energy should only depend on the angle. How much is that spring, how much is that bar rotated, so therefore how much energy you're storing in that spring. So my strain energy should just depend on my angle. Now, we know that to calculate the total potential energy, we need to take the strain energy and add to the potential of the loads, which is another way of saying that is because the potential is the opposite of the work being done, and we can subtract the work. Now, what's the work in this case? The work is going to be the force times the displacement, which is the displacement's not really obvious, but it should depend on our angle. So I'm going to say, let me break this out and say, oh gosh. Force times distance is work. Potential is the negative of the work, so hence the negative sign. The force is obvious, we're applying the force. Displacement is not obvious. So we have to do a little bit of geometry to figure out what the displacement is going to be. So this is the total potential energy. We haven't really figured out what U and what delta are yet, but we can do that next. U is pretty simple. Rotational springs act the same way as linear springs. It's just that the units on the spring stiffness, K, are different. Normally K is force. Now we have a force per unit length here. And so this is really simple. My U of theta is equal to 1/2 K times our angle squared. So normally we're used to 1/2 kx squared. In this case, just the units of K change, the form of the strain energy stays the same. P is given, it's what's applied. Delta is a little bit tricky, so let's just do some geometry here. So what we want to find is this thing. So we can kind of redraw this and say, okay, if that's my initial height, well, we won't do that. We'll say this. We'll say, let me try this again. Sorry. I'm going to color my cantilever purple, and then I'll use green for the rest of my triangle. So this height here, this length is L. And so this length was L. That's where it was initially. So my rotated cantilever went from the green state to the purple state. It rotated by an angle theta. And what we're interested in is the vertical deflection. So what I mean by that is how much did it go down? So we need to find so this height to this height is delta. That's the vertical deflection. Or I guess I called it capital delta, didn't I? Sorry, let me change that. That's how height is capital delta. That's what we want to know. If we know capital delta, we can plug it into our work and we can move forward. So we know that this height to here is going to be just like before, L cos theta. And so my deflection, delta, is going to be the length, L, minus L cosine theta, right? The total height here is L. I just care about the vertical deflection because that's what the work is doing. The work is causing a vertical deflection. I just care about delta, and delta is going to equal this total length. Let's draw it more clearly. Delta is going to be L minus L cos theta. And so therefore, if I factor out the L's, I get this expression for my deflection. Sound good? Okay, take a second and see if you can calculate the equilibrium configuration. What you want to find is P is a function of theta. Okay, do people get here? I want to pause here for a second because you're going to notice something that's different than the pendulum problem. And the thing that's different from the pendulum problem is that, for one thing, theta equals 0. If we set theta equal to 0, this equation is solved trivially. So one solution is to say, look, the cantilever never deflects. That is an equilibrium configuration. So one option is theta equals 0. Another option is we can pretend that we don't know that and just say, well, I have an equation here. I'm really interested in knowing P as a function of theta. So I will just ignore this and solve for P. Did folks get to that part? If you did, you probably got something that's P is a function of theta is equal to K times theta over L sine theta. It's an algebra. Not too bad, right? So if you remember in the review paper, I talked about there's kind of two fundamental instabilities, buckling and snapping. And the primary difference between the two of them is that buckling has 2 or more equilibrium paths. And what happens is you start on one path and you typically switch and jump to a different path. So here, look, we have two options. Either we can stay undeflected forever, or we can always deflect, or some combination of the two. And we have to evaluate the stability of these equilibrium configurations to determine what's going to happen. So let's do that. Take a second, calculate the second derivative of your total potential energy, and see if you can determine how stability is set for the system. All right. So what you find, let's see, is that the second derivative of my total potential energy with respect to my angle is equal to K minus force times the length of the cantilever times the cosine of my angle. And what I'm interested in knowing is when is that greater than 0? And so here you see I have two terms, and the relative magnitude of these two terms is going to tell me whether I'm stable or not. So when I have two terms and I have to figure out Well, when is one term going to be bigger than the other? You just, instead of setting this thing greater than equal to 0, you just set it exactly equal to 0 and say, when do these two terms equal each other? And then I will know if the force is larger than that, this term will be dominant, and then therefore will be negative. And if the force is smaller than that, this term will be dominant, and then therefore I will be positive, so stable. So if you want to find out the competition between these two terms, first set them equal to each other, or set this thing entire equation equal to 0. And let's first check this configuration here. So if we choose theta equals 0, why are we picking this one? Well, that's where it started. So we might as well start with the configuration that it started in and say, what happens if I start here and start loading on it? If theta is equal to 0, cosine theta becomes 1, and then I am left with k minus PL equals 0. I can solve for P. Therefore, another 3 little dots. There is a transition. There we go. That occurs at this critical load. Think about what this means for a second, because it's kind of the crucial takeaway from all of this. It means the cantilever starts with an angle of 0. I start pushing on it. Angle of 0 is the stable configuration for this cantilever until the force I apply reaches this value. At that point, this becomes an unstable pathway. So we can draw this. We can say, okay, I have a P this is my force P, this is my angle theta. The beam can buckle to the left and to the right, and so we have to have kind of this thing centered around 0. And what our equation is telling us is that there's a point at a value of k. Oops, can't really see that, can you? At a value of k over L. This is a tricky force displacement curve because it's really weird for us to visualize. Usually we're used to force displacement curves that are like linear. I push on something and I see like this slope increase. In this system, it's a little bit different. What's happening is I push on my cantilever. My force goes up, but my deflection doesn't change at all until I get to this point. So this purple bar here is stable, right? Because this value is greater than, this quantity is greater than 0 as long as this P is less than this load. So that means this quantity is greater than 0 with no deflection as long as this load is smaller than k over L. Once I get to k over L, the sign changes, and this pathway that's going vertically becomes unstable. That's terrible. I'll just draw them as checks. Stable up to here, unstable. So now what does it do? Well, it picks the other pathway. There's another option for it. Now it says, well, now my force is actually going to vary in kind of a pain of a way with theta. This is a really simple system. This is like a rigid bar with a spring. And you can already see the appearance of a term that came up in that review paper quite a bit. And that's the appearance of a geometric nonlinearity. What I mean by that is there is a nonlinear force displacement response that has nothing to do with the material. I haven't told you anything about the material. It's a rigid bar. It's nonlinear because of the geometry of the system. So what that means is I can plot this theta over sine theta. I imagine no one knows what it looks like. It sort of looks like a really soft parabola. And so what that means is it kind of does that. Oh no. Where the force will go like this. I push on my cantilever, I get no deflection, no deflection, no deflection. Now the cantilever buckles, it goes left or right. We don't know, depending on imperfections, infinitesimal issues in which are you really loading it at the center of the cantilever, or are you off by like a micron to one side of the left or the other? In that case, it either buckles left and then the force increases by this equation, or it goes, or sorry, right or left. I should do this on my thing, shouldn't I? It goes up, no deflection, buckles this way, or buckles this way. Oftentimes with stability problems, and I talked about this in the review paper too, we chatted about this as well, is we talk about linear stability analysis, linearizing things. And that's because this is the simplest possible problem, and A, it's already nonlinear. You can imagine that adding any other thing to it, like a beam that can deflect, or something that's going to buckle into an arch instead of there's a rotated thing, is just going to increase the nonlinearity of it to the point where you probably can't solve the problem anymore. So what people do is they say, well, what if we just get rid of this nonlinear term by assuming the deflection will be small? This is the mathematical equivalent to what you've done 1,000 times in your career, which is saying small angle approximation. Small angle approximation is simply the first term in a Taylor series expansion around theta. So if I Taylor expand sine theta, I get sine theta is approximately equal to 1. Is it minus or plus? I think it's plus theta. Nope, sorry, just kidding. I did it wrong. That's cosine. This is going to be equal to theta, and then I can never remember if it's plus or minus. What is it? Say plus. Check this. Theta cubed over 6. Taylor series expansion, right? It's like first derivative of your thing times the 1 over that n factorial. Small angle approximation says just keep the first thing, which is theta. If I linearize this equation, what that means is grab only the linear term, approximation for sine. I keep going to the board. That means just take this thing and ignore this and all these higher order terms. And you can see if I do that, then my force displacement response or my force angle response changes from something that's messy and nonlinear to theta over theta that cancels out. I get a horizontal bar. So you would often see it drawn like this. Linear stability analysis helps you find that critical point, helps you find K over L, but doesn't tell you what happens after K over L. That's the trade-off. It's like you made a deal with the devil. It'll tell you when it's going to buckle, but it ain't going to tell you what's going to happen. For that, you need to do more work. So linear stability analysis allows you to find out, is my structure in a stable equilibrium or is my structure in an unstable equilibrium? I want to know when it switches from stable to unstable. When does it lose stability? And here it loses stability at K over L. There's all sorts of things you can do here. Again, going back to the evaluating higher order derivatives. And you could ask, is this point, the red dot I drew, is that point stable? Can it sit at K over L? Or will it buckle before it gets to K over L? So if you're loading it, will the system allow you to get to a force of K over L and then buckle after you get past that force? Or will the system buckle before then? This might seem like a subtle thing of like, who cares like how close you can get to the critical point, but in fact, it really changes the nature of that stability problem. For instance, buckling bars are it's kind of a smooth transition, right? Like I just kind of push on this and then it just starts to grow. My buckling amplitude is pretty subtle. Compare that to standing on a soda can. It can handle your load until it just gets to that critical point, and then it collapses catastrophically. Buckling is what's called a stable, it's actually called a stable symmetric bifurcation. It's stable because this point is stable. K over L is stable. You can get there, and it won't completely change character before you get there. It's symmetric because it doesn't care if it buckles one way or the other. It's fine. And it's a bifurcation because it looks like a fork, I guess. But you're really kind of applying a load, you come to a fork in the road and it has to choose. Instead of going straight, it goes off to the side. So it's a stable symmetric bifurcation. The can buckling problem is a very different beast, and it's unstable, and that instability at that critical point is really sensitive to any tiny imperfection that you can possibly add to it. These ones are kind of robust. I mean, I have like literally a hole right here, and it's not going to change how much this thing is deforming. Your soda can, and importantly, beyond that, I mean, so this problem of being able to predict the buckling of simple structures has like haunted structural engineers for like 70 years. Like for instance, a spherical vessel, just like a sphere basketball. We can write down, we can do the math. It would take us a while. We can do the math and tell you exactly what the critical buckling pressure is for that spherical ball. And if you were to go in lab and measure the buckling force of this bar, it would be almost exactly what the theory predicts. If you were to go in lab and measure the buckling force of a spherical pressure vessel, it would be wrong, like magnificently wrong, like wrong by 80%, and in the bad way. It like you say it's going to buckle at a pressure of 1, and it buckles at a pressure of like 0.2 or 0.1. So this is so bad that to the point where NASA basically has said, to hell with the theory, we're just going to put a fudge factor in front of the buckling load and say, whatever you say it's going to be, we're taking 20% of that value. And only recently have structural engineers started to figure out how to actually predict the buckling load of a spherical pressure vessel. This is really important. You think about SpaceX and NASA shuttles. I mean, they're all cylinders. They have the same problem as spheres. Same problem. You can't predict the buckling load. So all vessels that are going in outer space are cylinders with spherical caps on each end, or they're like just a spherical capsule that's being, designed for re-entry. They're very simple structures, and the buckling load, which we can't really predict that well with theory until very recently, and two, when they buckle catastrophically. They don't buckle like this, they collapse like a soda can. So getting it wrong is a huge problem. So the subtleties of these things are still kind of ongoing and active research on structural mechanics, because this problem is immensely challenging. How do you handle imperfections? Especially if you can't. It's almost like what you really want to do is say, I've made a spherical pressure vessel, let's buckle it, figure out when it buckles. But then you do that, and what happens to your soda can? Your soda can can't be used anymore. It's got plastic deformation, it's completely destroyed. So you have to kind of predict the buckling force without poking it too hard. It's very hard. These issues of stability and equilibrium are really kind of at the heart of structural mechanics. You need to know if your structure system is in equilibrium, and you need to be able to determine the stability of these systems. The last remark I'll make on this is like a word of caution to those doing like finite element modeling in any kind of commercial software, console, abacus, or whatnot. And the reason is because if you look at this graph, this is an equilibrium pathway. What breaks the symmetry is some sort of an imperfection. And oftentimes, if you ask the computer to just solve this problem for buckling, and you set it up perfectly, it'll just never buckle. It'll just go all the way up here, because this is an equilibrium solution. You've gotten trapped in a local minima. You don't know, unless you kind of perturb the system a little bit, you like literally poke it, that, oh my gosh, there's a lower energy state and it's over here. And so it's going to buckle. So your finite element code can predict that something won't buckle. And what people end up doing is they have to go into their structure, they go into their console model, and they start to add a little bit of imperfection to it. So they'll say, I'm not looking at a flat sheet. I'm looking at a flat sheet where I add a sinusoidal undulation to the sheet that is like nanometer scale. Doesn't matter. Like just something so tiny you would never see it. But you add it to your code, so that way you've broken the symmetry of the structure. You've kind of added imperfections to it. So now when it gets to this point, it buckles. This is just a subtle point to keep in mind as we as a society rely more and more on these computational models. You have to know what you're putting in, because what you're putting in is going to, the computer's not wrong. I mean, this is an equilibrium path. We just, in real life, nothing is perfect. And so whether it's the load or the material, something is going to break this symmetry and cause it to buckle. I want to stop here, but I want to move on to the snapping problem next class. Snapping problem is not that hard conceptually, but the math is a bit of a pain. And so I think we can use this as an opportunity to see if you can all download Mathematica onto your laptop. It's free. BU has a license, you can download it. And bring your computer to class if you're here, or otherwise if you're remote, be ready to work with Mathematica. I will give a kind of a crash course on how to use Mathematica. And I'll give you the crash course Mathematica notebook so you can play with it on your own. And then we'll do a very bare minimum of solving the snapping problem there. And I will try to convince you, your life as a BU undergrad to this point has convinced you that MATLAB is the king of all things. I'll try to convince you that Mathematica has a lot of really powerful tools to offer, especially with stuff like doing mathematical calculations and then having it spit out something that looks like this. That's what Mathematica is for. I want to take the derivative of my function, but my function is really messy. I want it to spit out something that looks like this. That's a mathematic you can do. You can make plotting, graphing, doing calculus so much easier than doing it. If you're using Wolfram Alpha, that's the backbone of Wolfram Alpha is Mathematica. So yeah, so we'll dive into it and we'll try to solve the snapping problem next class. Homework due tomorrow. I guess just get it to me by the end of the day. And otherwise, yeah, take care. I'll be on office hours later. I'm happy to answer any questions. So thanks, everyone.